Good morning and welcome to the 2016 competition for the Daniel H. Wagner Prize for Excellence in Operations Research Practice. This prize is sponsored by the Informed section on practice and was established in memory of the late Dr. Daniel H. Wagner. For those of you who did not have the good fortune to know Dan Wagner, he earned his PhD in mathematics from Brown University in 1951. And although his formal training was as a pure mathematician, upon graduation, he joined the Navy's Operations Evaluation Group at the Pentagon, working on operations research for naval warfare until 1956. After a one-year leave of absence for postdoctoral research at MIT, Dan joined Burroughs Research Center, and there he directed a group of mathematicians performing analysis for the development of digital computers. That turned out pretty well. In 1957, Dan's entrepreneurial spirit took over, and together with John D. Cattell, he formed the partnership of Cattell and Wagner, which was subsequently dissolved in 1963. That same year, he formed a new company, Daniel H. Wagner Associates Incorporated. This company applied itself to leading-edge work in the mathematics of naval tactics, especially anti-submarine warfare, detection theory, and search planning. During his years as president and principal owner of Daniel H. Wagner Associates, Dan brought many high-quality mathematicians into the operations research community. This led to significant advances in the firm's fields of endeavor and delivery of significant applications to the Navy, Coast Guard, and other clients, many of which applications are still in service today. After retirement from the firm he founded, Dan continued his commitment to the field of operations research, serving in various teaching and research positions with the U.S. Naval Postgraduate School and the U.S. Naval Academy. He was an active member of ORSA and then Informs for more than 40 years. The idea for this prize began at Dan's memorial service in April 1997, where many of his former colleagues gathered. It was made possible by generous endowments from the firms Metron Incorporated, Daniel H. Wagner Associates Incorporated, and Applied Mathematics Incorporated. I am Alan Butler, the chair of the prize committee and the president and CEO of Daniel H. Wagner Associates. I am indebted to the judges for their hard work in this year's competition. Those who were unable to be present today participated fully in the judging of the papers. The members of the 2016 prize committee are Bill Browning, Ann Bixby, Terry Harrison, Kathy Lang, Patricia Neary, Alexandra Newman, Randy Robinson, and Larry Stone. Throughout the day, we will have 6 finalist presentations of 30 minutes each, with 10 minutes each for questions. Judges will have first priority for questions. If time avails, we will allow questions from the audience. Please do not interrupt the presentations for any reason. You will notice that these presentations are being videotaped, so I ask that you turn off your cell phones and remain in your seats until the conclusion of the question period. And now, from the Université Laval, Quebec, Canada, Michael Ronquist.
So, Mr. Chairman and jury member, and ladies and gentlemen, we are very happy here today to present the Calibrated Route Finder for you. And the presentation today will be given by Gert Andersson, who will be representing the Swedish Forestry, and myself, Mikael Rönnqvist, who is sort of representing the team. And we should also acknowledge that there are many people and organizations who have been supporting us in this development. And also before I start, I want to stress that when we did the development of the system, and a really sort of important aim with the system has been to find transparent and fair systems that really take care of the people, the environment, and the safety, and at the same time maintaining a competitive edge for the Swedish forestry. So the outline is we will give a short background, describe the problem. We'll give a historical development of the various operational research components. We describe the system, its impact, and finish off with some concluding remarks. And we will start this one with the movie describing the feature.
This is Mikael Skogland. He's the owner of Skogabu, a trucking company that has a total of 5 timber trucks and 10 employees. Mikael and his colleagues are running about 900,000 kilometers each year on every kind of road, from fine paved roads to roads which look more like a path. Mostly, timber transport happens in the famous home districts, but it is quite common to have return cargoes in unfamiliar new areas. Often there are many difficult choices. What's the best path? The least stressful? And which route saves more fuel? It is easy to make wrong choices. Sweden's thousands of drivers have a particularly complex job. Each ride is a balance between cost and time, security and safety, regulations and ordinances, often under psychological pressure and varying weather conditions. Additionally, they are responsible for large values. Every year there are 2 million timber transports from 200,000 new landings to over 1,000 industries and railway terminals. Payment between truck companies and forestry companies are agreed upon for the distance driven. In the past, there have been many different methods used to calibrate distances, often with large inequities in payment when drivers drive between different companies or different areas. That is the reason why both truck companies and forest companies want to establish a more fair, transparent, and efficient system for standardized distance measurement. Therefore, forestry research teams, forestry companies, the haulage industry, and SDC in the year 2009 decided to jointly start the project Calibrated Route Finder. The system is based on a number of large and complex data sources and takes into account all aspects that drivers and businesses consider important. Development and improvement of the system is ongoing.
As you saw in the movie, we have a lot of small and narrow forest roads and roads, but we operate quite large trucks. The maximum limitation is 25 meters, 64 ton, and if you compare to rest of the Europe, there will be a maximum limitation of 18 meter, 40 ton. And the reason why industry wanted to develop this system is to help truck companies, forest companies to agree on the best route. And before the system, the typical discussions was, how long is the route? How short is it? Or is it a safety route? This is Sweden in Northern Europe. And this is an illustration of our logistical challenge. We have more than 200,000 landings, logging sites annually, the green dots. More than 1,000 mills spread all over the country, the red dots. And we have 5,000 truckers, drivers, operating the transport operation to a huge cost, $660 million US. That is 25% of the total truck freight cost in the country.
So the problem faced by the drivers is quite complex. So when are the landings, they really need to decide on the many objectives. It could be you need to minimize the stress, it could be the hilliness, it could be the length of fuel consumption. So there are many aspects. So the question here is, should I take in this case, the hilly road in the middle, or the curvy road to the right, or maybe the fast, nice road to the left, or maybe do a shortcut through the village up there. And the truck companies, when the driver comes to a landing, they need to have important information. And one is it possible to actually turn there when you have these really large truck? Another one is that the road system is classified in different levels. So the roads are classified from 0 to 9. 9 is the worst quality. So this is a quality 9 road. You can see it's very narrow. The best quality is 0 road. That's the European highways. And here you can see that the road is getting slightly better, but still it's not possible for other trucks to meet there. And of course it goes up in terms of quality. Typically when you use systems, you want to find, for example, the shortest path. So this is the shortest path between a landing and one of the mills. Another option would be to choose the fastest route, which is based on the speed limits on the road. So here you can have you can balance them. And this is a commercial system, what they propose for the best route to go to the mill. When we ask the drivers, they say, we want to take this green one, because the green one here is our best practice. So that's the one we want to have. So of course, when you have different objectives, it's always a balance. And what we can do is we can select different weights for the objectives, and we can create any of these red routes to be the optimal in the minimum cost route problem you need to solve each time. Of course, in our problem, the basic problem for us is really, how can I select weights such that when I solve the minimum cost route problem, I generate the green one, which is the best practice. So why is the best practice a better one? Well, here is a lot of data, but we can see that that one is typically a bit longer than the other one. And if we go to the details, this is the road classification I talked about. And if you look at the numbers, you will see that it really drives a longer distance on the higher quality roads. So that's a desired property. Another thing here is some of these roads are very narrow. So this is a 3 to 3.5 meter narrow road. It's impossible to meet any other truck. So best practice is not to run on those roads. But if you have another system, it might provide those. Another one which we come back to is curvature and hilliness. And here you can see that you really want to avoid curviness and hilliness. So these are some of the characteristics. Of course, there are more attributes too. So in the road database, there are 10 different road features used here. And each of those road features has a number of attributes. So for example, if we look at the road feature maximum speed, it has 13 different attributes corresponding to each of the speed limits ranging from 20 up to 120 kilometers per hour. So each of those road features has a number of these attributes. So when we look at the development of the system, so it really started already in 1990 when the government and the forest companies agreed to jointly collect data for a Swedish road database. And the forest company was responsible for all the private roads, government for the others. In 2006, it was decided to develop the system. And in 1 year later, we tried to set some manual weights, and that was deemed totally impossible. It just didn't work. So we spent a year to develop the methodology, which we're presenting here today, to do this optimally. And a year later, it was first put in production in 2009. So the system has been in production since that year. And over the years, we've been doing some it's been evolving over time. So 1 year, we really needed to look more detail on the routing in the cities. We had some problems with narrow roads. We looked at hilliness and curvature. We looked at sort of different weight restrictions on trucks, more detailed routing. And now we're looking at different ways to set up new agreements for the transportation. So it's been evolving over time. So what about the road database? Well, in Sweden, it's a large proportion of the roads are private. So it's about 2/3 of the roads are private. Now, the roadwork, of course, give rise to the network we need to do to solve the minimum cost route problem. So the network we need to operate online has 4.4 million arcs, 2.2 million nodes. So that's the size. So what we do now is we're just going to zoom in and look at some examples. This is outside one of the cities. So we're going to zoom into one of the roundabouts. So what you see here is each of these dots is a start and end of what we call reference links. Now, if we add also when you change speeds or when they're sort of overpath, what you have now is each of these dots represent the start and end of an arc in the network. So this sort of gives the detail level of the network. And of course, each of these arcs here has one of the attributes of the road features, a unique set. Now, when we add the geometry coordinates as well, we can compute hilliness and curvature as well as the two other road features. So this is an illustration of the level. So how did we do this? Well, when we started, we really needed to find some balance. So what we have is we have these 106 weights we need to find some weight for. So to the left, we have the different objectives, which again is like the curvature or fuel consumption, distance. To the right, we have all the data which is available in the road database. So we need to do a mapping between these. So we need to find the weights for the attributes. And for those who do multi-criteria, you probably know that if you set just 2 different objectives, it's quite tricky to find the balance. And we had 106. So of course, it was totally impossible. So in this sense, what is really important for the project is what we call key routes. These are the best practice routes. And best practice routes is that we went to the companies and collected detailed information on 1,500 individual routes, the best practice routes. So we have those really detailed, sort of mapped. And these are evolving over time as well. And here is just to illustrate that they are evenly spread over the country. They're also evenly spread among the companies. So with these key routes, what we have now, we really have the key for this translation. So what we have is we know that the best practice is the one we want to have the optimal solution. So our problem now is really inverse optimization. We want to find weights of these 106 attributes such that when we put those into the minimal cost route problem, they will generate these key routes as the optimal path. So this is an inverse optimization process, and in general, that's really to, given a solution, how can I find a minimal adjustment of the objective functions in order to keep that solution as optimal? In our case, it's a bit more complicated because we cannot sort of adjust each of these 4.5 million arcs. We need to adjust only the weights, the 106 weights. Also, it would be impossible for us to generate all the key routes as optimal. Also, the objective which we want to minimize need to reflect the multi-criteria problem faced by the drivers. And again, it's a very large graph we need to solve this problem over. So the first model we developed, really the key decision variables are the weights of these attributes. We also have binary variables to indicate which of the routes is the best one. So now we need to know that for each of these key routes, there is, of course, like I show in the other picture, the red ones, there are multiple potential routes. So in this model, we assume that we generate all those. So for each key route, it might be hundreds of thousands or even millions of each. So what we have now is we wanted to find some objective, and there was a lot of discussion, but we agreed on trying to find as many of the key routes as optimal in this problem. So that's the objective. What we have is, because we have information on each of the routes, by changing the weights, we can compare the points allocated to a key route and the points allocated to any of the other routes. If the key route is the best, we can put the binary variable to 1 and count it in the objective. If it's not, well, then in fact we need to find which of the others is the best one, because that's a secondary part of the objective. Of course, we just need to have one route per key route, and then they have some more practical limits on the weight settings. So we tried this model for about 3 years, but we noted that there are sometimes between different weight settings, it changed quite a bit. And it was hard to describe that for the drivers and the planners. So we aimed for a new model. In this new model, we really sort of just minimize the deviation in points between the key route and any of the others. And in this case, we just need to find the best one, which could be another one or the key route itself. So the problem now is, because we don't need to know which one, we just need to find the best one. It becomes considerably more easy. So this is a linear programming model compared to the other one, which is a mixed integer programming model. One of the main problems, however, is that, like I said, it could be, when we have all the key routes, it could be billions of potential routes. So it's impossible to generate them up front. So what we do is we start with our 1,500 best practice routes. We have a network. We have some initial weight settings, but typically from the last one. And then for each of the key routes, we generate the minimum cost route path. We add that to the model. We resolve either model 1 or model 2 to get the new weights. And then we do it again. We repeat and generate new routes. And we repeat this until we found the optimal solution. So this is a representation. So each of these cuts here represent one of the routes or alternatives in the network. So when we start with some initial weight setting, it might be at 0. We will generate in this picture only one cut, and then we're going to continue. We have new weights, and then we're going to generate new cuts until we generate the cuts we need to identify the optimal solution. So this is the progress. It's really a cut generation process, but we need to add some variables as well for the models. So to solve this one, the first model took about 1-2 hours to solve. The second one is 20-30 minutes to solve, and not too many iterations, and typically less than 4,000 variables or routes to generate to find the solution. When we started to use the system, the municipalities get a bit upset. Because what happened is that some of the routes we generated, it could be like this. This is one of the cities, and there is a mill close to the city, and there's a school there. and the municipality really wants to avoid passing these areas. So what we had to do is, with the sort of the transportation company, the forest company, the municipalities, is to define what's in pink here, what we call approach routes. So when the truck hits some of those routes, we need to follow those. So in order to implement that, we need to really sort of make some adjustments to the network, and of course collect all the information. So now when we do it, so the green one is the one which is going to be generated to avoid passing the school in this case. So each of the cities who have this, we need to collect information for each. Hilliness was another aspect that the drivers didn't like. They said that they were too hilly. So we needed to find some ways to measure hilliness and add it as a road feature. And typically when you look at these hilliness, the main sort of component is increased fuel consumption. And if you look at this table, there are some detailed measurements. So if you look at the bottom row, you will see that when it's about 6 degrees, the fuel consumption goes up by a factor of 5. So because we have all these coordinates, we can, for each arc, compute the increased fuel consumption. And then we make a discretization, in our case 10 levels, and that would become our feature as our attributes in the road feature hilliness. We do similar things for the curviness. So because we have the geometry coordinates, we can approximate radiuses along the road. So in the picture here, you see an indication of 3 different radiuses which could be estimated along the road. Of course, there could be many more. Now, when we have these estimates of the radiuses, we can use a formula which is used in Sweden for designing roads. Typically, what you do when you design roads is you determine the speed limits and then the radius, and you build the road according to that. So we use the formula in a bit in reverse engineering, because we have the radiuses and want to find the speed limits. And you might say that sort of doesn't make any sense. And for the government roads, it doesn't, because they are built for a certain purpose. But the forestry roads typically have a speed limit of 70 kilometers per hour. And when you run on those small roads, it's not possible. So having these sort of estimation gives us how fast they actually can run on those. So what we do is and this is an example, so you have a 70 kilometer per hour limit, and then 2 curves, one big and small, and then it's a 50K. So what we can do is we can define these profiles for each of the arcs. So when you are coming close to the curve, you need to brake down. And then in the curve, you need to run, in this case, 45 kilometers per hour. After the curve, you can start accelerate again. Then you need to brake for the next curve, run to the curve, then accelerate, and then you need to brake again before the 50K limit. So what we can do is we can define these profiles for each of the arcs. And then again, we make a discretization in relative increase in time, and that becomes our attribute to compute curviness. So another one is road intersection. So this is more detailed. So typically when you define a network here, you simply sort of add a node in the center, and then you have arcs representing each of the lanes for the road. Now, there's some issues here, because when you have a road with a steep angle, you will see that, of course, it's not possible to actually do the left-hand turn here. But because you're in the mathematical model, you have a node there. The mathematical representation allows you to do that. So we need to sort of make sure we can't do it. This is another one. Here you have what's called 2x1 road. There's a railing in the middle. So typically, if you you construct the network, there's a node at the end there, which means that in the mathematical model, you can turn, but in practice, you cannot. Another third example. So this is an example of forbidden left-hand turn. So you cannot turn left directly. You need to do a sort of off trip to the right here. And when most of the commercial systems, they have some way to deal with this type of turning. And the one we tested, they don't handle either of those we've been talking about. So we need to have more standard ways to do that. So in our ways, we use an augmented network where we sort of have many more nodes, and each turning alternative is represented by an arc. So now if it's not allowed, we simply take it away. Moreover, what we can do when we have that, we can also add waiting time at these crossings. So if you look at this picture here, the blue and the orange have very different waiting times in this case. And we can put that into the model. Also, turning left and right is a difference here for the orange.
Thank you. So the system is used by many persons and organizations. The truck drivers can use it the day before in the pre-planning of the coming routes, or even during a route during the day. The planners can use it in different horizons, the operational horizon or the tactical planning horizon. And the system is used to manage all the invoicing between all the different parties in our transport system. Here is the number of calls to the system from last month. It's like 20,000 calls per day. So I want you to know that the Swedish forestry is considered one of the most competitive in the world. And the Calibrated Route Finder helps us in our strive to even more increase productivity and quality in what we are doing. And here you can see that the system was introduced 2009, and the usage has increased to 60% of all the transport, and more than 100 companies are using the system. And it's increasing all the time.
Jan Gustafsson at Stora Enso Forest has been involved and a driving force in the joint development of both the Swedish Road Database and the Calibrated Route Finder, both as chairman of the Logistics Council, one of SDC's steering groups, and as head of strategy and business development at Stora Enso Forest.
Our jointly for the forest sector in Sweden is that every transport is paid out from the actual distance. And of course, for the parties involved, it's a lot of money in this, and it's very important that each distance are calculated, generated in an accurate and objective way. And if you look at the help we really get from the National Road Database and the Calibrated Route Finder, it's enormous what big step we have taken the latest couple of years.
And for Mikael and his company, work is now much easier, and he thinks that the risk to take the wrong route is minimized. This leads to much better use of time, in particular when he drives in new remote and unknown areas. They have increased the productivity considerably with the routes from the Calibrated Route Finder. The routes are also the same for all companies and drivers, which of course guarantees fairness among all of the companies. But it is not only about finding the best route for the driver in the industry, it is also about finding the best way for the environment and people along the road. Mikael says that an advantage today is that they avoid passing schools with narrow and low speed roads. They are routed around such sensitive areas on roads better suited for heavy traffic. This is a very important development for safety as well as the working environment.
Really important is that the higher transport efficiency contributes to a better environment by less fuel consumption and CO2 emissions. By the Calibrated Route Finder, we have got an excellent tool for control and balance the real important transport issues: costs, environment, and traffic safety.
So when we look at the traffic safety, it's quite difficult to measure that. So what we've done is we did some trials here. So what we have the Calibrated Route Finder, and we compare it with the route which will be given by a shortest path or fastest path. So what we have is we have a number of these attributes. So when we look at some of the attributes which relate to work stress, it's really to drive on the low quality roads or narrow roads or roads with a high level of curvature. So we can see that the improvements are in the range of 20 to 80% in distance for those. When it comes to safety, it's more on the 30 kilometer per hour limit or in the routes which are in the cities. And here we can see sort of typical improvements between 20 and 60%. We can also, besides meeting these sort of safety aspects, we can also save, in addition, some on the cost. So typically, an average sort of transport is $390. And if we assume that we have the 60% of the total transport, we save about $5 to $7 million each year, and increase productivity as well. We also sort of lower the CO2 emissions by 16,000 tons. And because of the system, we can really do the collaborative logistics, where you have another sort of big part of potential savings.
At Sveaskog, we have used Calibrated Route Finder since 2011. We transport 9 million cubic meters annually, which is 12% of all forest transportation in Sweden. Our experience together with all our haulers is very positive. The distances are very accurate and the administration work is substantially lowered. Calibrated Route Finder balances objectives as traffic safety, stress, economy and environment. This has led to a paradigm shift in how to determine routes and distances. There is no other system for logging transportation that can meet our high quality requirements regarding efficiency and transparency.
Calibrated Route Finder has been in production at the STC since 2010 and has successfully replaced all the systems that were regarded as unfair and with too much administration work. The information in the roads database is updated daily, and the production system has 4 revisions during each year. Before any development is implemented in production, prototypes are analyzed, tested and verified extensively. The number of companies using Calibrated Route Finder increased continuously, and today more than 100 companies use the system. Our final goal is that 100% will use the system for automatic invoicing and routing.
So I'll sort of will stop here with some concluding remarks. So the general contribution of the system is that we really managed to balance the different objectives, including the safety, stress, cost, and environment. And it's really a paradigm shift in how to find the route. And you can really see it as a social contract, which is sort of really to get a socially acceptable route for all the society. It's also a transparent and standardized system. It enables a better use of transportation resources, and it enables collaborative logistics between different companies. And more specifically for the operation research contribution, so we have this innovative inverse optimization for balancing best on best practice. We have an efficient method to solve each of those models we need to solve to get the weights. We have a novel inclusion of the hilliness and curvature as road features directly in the road database. We have these special routes for dealing with the routing in cities or nearby. And we have these detailed sort of routing when we really want to look at the fuel consumptions and time delays. And also, to finish off here, so it's really important that the system can be used by either planners, drivers, and they typically don't have any operation research background, but they do have an understanding how it works because they are faced by the system every day they're working. So, and then these are just some key numbers of the use today, and I was talking about these before, so we will stop here and take questions. Thank you.